graduate student at Queen's University studying astrophysics. In particular, I study cosmology, which is the study of the origin, development, and ending of the universe. In particular, my research looks at inflation, which is the exponential expansion of the universe a fraction of a second after the Big Bang. There are many reasons why we believe inflation happened, and one of the most compelling reasons is that the universe looks the same everywhere at large scales. We can take photos of the universe from when it was 300,000 years old all the way to today, and in all these photos, the universe looks the same everywhere. Here's a map of the galaxies in our universe taken by the Sloan Digital Sky Survey, or SDSS. Each dot on this image represents a galaxy. Notice that there's this web-like structure that looks the same no matter where you're looking. Also, note that there's these black wedges. The only reason those aren't mapped is because the dust of our own galaxy, the Milky Way, obscures the view of the distant universe in these directions, not because there aren't galaxies that exist there. Next, I will show you a photo of the universe when it was 300,000 years old. We can take photos of this time period because light travels at a finite speed and takes time to get to us. But first, consider a map of the Earth. We know that the Earth is a sphere and is three-dimensional, but we can project it down to 2 dimensions, or like a piece of paper, and look at a map. So on the screen is a map of the Earth, where we know it's three-dimensional, but we're looking at it in 2D. Well, when we try to measure the universe when it was 300,000 years old, or more commonly known as the cosmic microwave background, we're taking measurements outwards from all different points on the Earth. So we're getting a sphere of this data. And just like with the Earth, when you have a sphere, you can look at it on a map in 2 dimensions, you can do the same thing and get a map of the cosmic microwave background in 2 dimensions. So on the screen here is this map of the cosmic microwave background. Notice that there's no structure and everything is at negative 270.4 degrees Celsius. If the average temperature is subtracted off of this map, we're left with really tiny temperature changes on the order of microcelsius, or 0.000001 degrees Celsius. This is super weird, and I'm gonna try to explain to you why. So imagine you are having a potluck, and you invited 2 people over, and they both showed up with potato salad. Well, it's a little weird that they both showed up with potato salad, but you can just dismiss it as a coincidence, even though they had thousands of dishes to choose from. But now imagine you invited 1,000 people over, and every single one of them showed up with potato salad. Not only did they all show up with potato salad, they showed up with the exact same amount of potato salad. So 1.000001 kilograms of potato salad. Well, you can't dismiss this as a coincidence anymore. They must have all been in contact before this potluck and decided to play this hilarious prank where they all brought the exact same amount of potato salad. Well, that's just like the particles in the early universe. They must have all been in contact with each other beforehand to all be at the same temperature at the cosmic microwave background. Next, I'm going to do a demonstration to show you how inflation solves this problem. All you need is a glow stick, some balloons, and a timer, or a phone that has a timer on it, or a computer that has a timer on it. So, we're going to take the your glow sticks and turn it into a circle like this. This will represent the border of the cosmic microwave background. The balloons are going to represent the universe. We know from taking photos of this cosmic microwave background that everything's the same temperature, so it must have all been in contact with each other before. If normal matter, so the stuff that makes up you and me and this table, was dominant in controlling the expansion of the universe, it would expand really slowly and wouldn't fill up this entire cosmic microwave background. It would look kind of like this. So we're going to set our timer to 5 seconds, and we're going to blow up our balloons very slowly to represent normal everyday matter. Okay, so 1, 2, 3. Great, now you can tie off your balloon. So this is what our universe would be like if just normal matter caused the expansion. And when we compare it to this cosmic microwave background outline, it doesn't fill up the whole thing. So our universe couldn't possibly all be the same temperature because, as we said when we talked about the potluck, all these particles must have been in contact beforehand to all be the same temperature. and it doesn't blow up to the correct size. Next, we're going to consider a period of inflation. So we're going to have this balloon expand or blow up really, really fast at the beginning, and then slowly expand like if normal matter was in charge. And we're going to see if we can get it to the same size as this. Okay, so again, set your timer to 5 seconds, and we'll do this again. So remember, really, really fast at first, and then the normal slow speed of normal matter. And then we're going to tie it off. So we had that really, really fast initial burst and then the slower burst. And when we compare it to our cosmic microwave background, they're the same size. So this period of really, really fast expansion at the beginning, or inflation, makes it so our whole universe could have been in contact early on, and we can explain why everything that we measure for the cosmic microwave background is the same temperature.